Hello students, welcome back. In this video we start chapter 9, which is inferences from two samples. Chapter 9 section 1 is dealing with two proportions or two probabilities. So the new concept here is up until this point we have only dealt with one set of data at a time. Chapter 9 involves making inferences about two sets of data at a time. So just a conceptual example, we won't actually solve this problem right now, but just so we can kind of get the terminology down for what we mean by dealing with two sets of data at a time is accuracy of a fast food drive-through order. And we're dealing with a Burger King drive-through order, and then we have total orders that were accurate and not accurate, and then McDonald's, how many orders we analyzed and how many were not accurate. And then we are making a claim that says Burger King and McDonald's have the same accuracy rates. And then we are doing a hypothesis test on that claim. So we are doing hypothesis testing, dealing with two sets of data. Okay, so we kind of just talked about this slide right here, and we are going to be doing it with confidence intervals as well. So we'll be doing hypothesis testing, both p-value and critical value, and then we are also doing confidence interval. So we are building on what we already know from chapter 7 and chapter 8. And here is just the notation for dealing with two proportions. So we just use the subscripts to describe which data set we're dealing with, the first one and the second one. So P1 will be the population proportion for the first one. P1 hat will be the sample proportion, which would be the number of successes over the total number in sample 1, and 1 is the size. Q1 hat is going to be the complement of P1 hat. And then just note that for the second data set, you just have a subscript of 2. Okay, so since we are analyzing two samples at once, we want to combine the proportions from each data set in order to make a single inference. So we're taking the two, and then we are doing an equation to really be able to analyze one number at a time, which incorporates both the proportions. So we call that the pooled sample proportion, and that is denoted by p bar, or p with a line over it, and it combines the two sample proportions into one proportion, as shown here. So p bar is going to be x1 plus x2 divided by n1 plus n2. Nothing too crazy. So the requirements are the same as previously, only now we're dealing with two. I don't need to read all of them, but quickly, that they must be simple random samples, they must be independent, and then you must have at least 5 successes and 5 failures. So in chapter 8, we had the test statistic z was found by this equation right here. Now, when we're dealing with two proportions, the z equation becomes this equation right here. So a little more complicated, and we can also use technology to get this value for us, and I'll show you how to do that as well. So as in chapter 8, we can use both the p-value and critical value to test claims about proportions. And then we can also use confidence intervals, and then we'll talk shortly about which one's preferred. So the confidence interval is going to be looking at here, and then the confidence interval estimate is that P1 minus P2 equals 0. When we do an example, that'll make a little bit more sense, but we're looking to see if we are going to be having our interval cover 0. Because if it's a positive number and then a positive number over here, we know that we are not covering 0. Same if it's a negative number over here and a negative number over here, we're not passing 0. If it's negative here and a positive here, we are passing 0. And that's ultimately what we will be looking at. Here's the equation for your margin of error. And similar to chapter 8, here is your interval right here. It's going to be P1 hat minus P2 hat minus the margin of error is going to be this right here, which you're usually going to be having at 0, and then the upper bound limit. So the p-value method and the confidence interval are not going to be the same here. So the p-value method and the critical value method are equivalent. The confidence interval is not equivalent. A lot of times you'll get the same answer, but you cannot rely on it being exactly the same answer every single time. So for the hypothesis test, we are going to let the null hypothesis be that P1, the proportion of the data set 1, is equal to the proportion of data set 2. So without further ado, let's go straight to an example, and we will solve this example several different ways. We're going to show you how to do it with the p-value method, the critical value method, the confidence interval, both with and without technology. So I tried labeling it pretty clearly so you know which way we're doing it, so you'll be able to solve it in the method that you prefer. So Connecticut and New York are contiguous states, both having laws that require front and rear license plate. The proportion of Connecticut illegal cars with rear license plate only is 239 over 2,049, or 11.7% of the cars are illegal in the sense that they only have a rear license plate, not a front one. So the proportion of New York illegal cars with rear license plate only is 9 cases of illegal over 550 analyzed cars, or 1.6%. The sample percentages of 11.7% and 1.6 are obviously different, but are they significantly different? Like, do you have enough data and enough information to make the claim the proportion's the same in both Connecticut and New York? Can you make that claim? We have to do a hypothesis test to test that claim. So let's kind of make a quick little chart. We have Connecticut, we have New York. Cars with rear license plate only is going to be the 239 out of 2,049 total, making the cars with both front and rear 1,810, and then here are the New York numbers as well. So the P1 hat or the is going to be 0.117 for Connecticut, and then P2 hat is going to be 0.016. We will use a 0.05 significance level to test the claim that Connecticut and New York have the same proportion of cars with rear license plate only. So the solution, first you got to do the requirement check, blah, 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 blah. Requirements are satisfied. We're good. So again, we're going to solve this 3 different ways and see how our answers compare. So first, we will solve it using the p-value method without technology. So step 1, we are just looking at P1 equals P2. And if P1 equals P2 is false, then P1 does not equal P2. The null hypothesis needs to have an equality, so we need to use the equal sign here. So we'll let the null hypothesis be P1 equals P2, and the alternative hypothesis H1 be P1 does not equal P2. The significance level was specified as alpha equals 0.05. So now we need to get the pooled sample proportion right here. So this is where we're using the data from both to make one single P and Q value. So we have our P bar equals 0.0954, blah, blah, blah. And then our Q bar being the complement of that, so 1 minus that. So it's either this value or this value. When you add them together, you get a total score of 1. So here is our test statistic right here, and we are assuming the null hypothesis, and that's what we were testing against. So P1 minus P2 is 0. So we have this equation becomes all of this long process to type into your calculator, but it's not that complicated a formula. Really, your biggest challenge would be typing into your calculator without any mistake. But when you put it all into your calculator, you get a test statistic of 7.11. So this is a two-tailed test because we have our alternative being a not equal to symbol. So the p-value is twice the area to the right of the test statistic. So we refer to table A2, and we find that the area to the right is 0.0001. So p-value is going to be 0.0002, double this value right here. So this is what we are looking at. And because the p-value of 0.0002 is less than the value of alpha is 0.05, we reject the null hypothesis. So if we reject the null hypothesis, we conclude that there is sufficient evidence to warrant rejection of the claim that P1 equals P2. That is, there is significant evidence or sufficient evidence to conclude that they have different proportions. Okay, now let's solve this a much easier way using our TI-84. So you're going to hit Stats, go over to Tests, so hit the right arrow twice, press 6 or just hit the down arrow until you highlight 6 to probability or proportion z-tests, and then enter your 4 values right here, your x1, your n1, your x2, your n2, and then what kind of tail test you're going to be doing. Highlight the calculate button and then press enter. So you should get the following results. So we get a test statistic of 7.107. Remember, we got 7.11 when we calculated by hand, so showing that it's the same value. Our p-value is 1.190475 e to the negative 12, which you should know is times 10 to the negative 12, meaning it's a extremely small number, essentially 0. So because the p-value, which is essentially 0, is less than the significance level of alpha, once again, we reject the null hypothesis. Also, you should know that your textbook shows you step-by-step how to use various softwares to solve these type of problems. We did the TI-8384. You can use Excel, you can use StatCrunch, or any of these other ones. Okay, now we will do the critical value method. So up until now, we solved this problem using the p-value method both with and without technology. So the critical value method can also be used. The first few steps are the same. So now we will refer to table A2 with a significance level of alpha is 0.05, and we find that an area 0.05 divided equally between the two tails corresponds to critical values of plus or minus 1.96. So drawing your bell curve, plotting your points where the z values are, and plotting our test statistic, we are in the green area, so we again reject the null hypothesis. The conclusions are the same. See, 7.11 is way, way, way out here, and our value starts right here. We are in the green area. We reject the null hypothesis. So now we will use the same data to construct a 95% confidence interval. So same problem, now we're looking at it with a confidence interval method. And we will do this both with and without technology. So first, without technology, to show you the thought process, with a 95% confidence level, we have our z-score of 1.96, and then we have to calculate the margin of error using that formula right here. And then we get a margin of error of 0.017482. So once we have that, we can know how to find our P1 hat and our P2 hat, and then get the difference right here. And with your margin of error, following this formula, you ultimately get an interval that says that your P1 minus P2 is going to be bounded between 0.0828 and 0.118. Again, these are both positive numbers, so 0 is not going to be somewhere in the middle. So the confidence interval limits do not contain 0, suggesting that there is significant difference between the two proportions. So this also leads to a rejection of the claim that they have the same proportion. Again, the real kicker that we're looking for is this value negative and is this one positive? If it is, then we cannot reject the null hypothesis. Since they are both positive and 0 does not fall in between the lower and the upper, we can reject the null hypothesis. So finally, just showing you how to do the confidence interval method with technology, show you how much easier this is. You hit the stats button, go over right twice until you go to tests, scroll down to where it says B2 proportion Z INT for interval, press enter, and then you're going to have this screen come up. So you type in your 4 values. Your confidence level is going to be a 0.95 as was specified. highlight the calculate and press enter, and then you should get this value right here. And again, these values right here are going to be the same as what we got when we did it by hand, or very close to. And once again, you come to the same conclusion that there is sufficient evidence to reject the claim that they have the same proportion. So we solved the same problem several different ways and came to the same conclusion.